Welcome to clickmyproject.com. Here we are going to discuss about the efficient register renaming and recovery for high performance processor. In our project we propose here achieving high performance in modern microprocessor requires a combination of exposing a large amount of instructions level parallelism and processing instructions at a high clock frequency. Exposing maximum ILP requires the processor to concurrently operate upon a large number of instructions, also known as an instructions window. Hardware structure to buffer these instructions must be sufficiently large. However, high clock frequency requires frequently accessing structure to be small and fast. With increasing clock frequency, new designs that do not require the large cycle critical hardware structure become necessary for building large instruction windows processor. This project presents a detailed study of performance issues related to large instructions window processor and present a novel and efficient checkpoint processing and recovery microarchitecture for such processor. In this project, steps of a microprocessor critically affected by the demands placed by a large instruction window, the need for a high frequencies, the scheduling window, branch misplacement recovery mechanism, the store queue, the physical register file, the mechanisms size and access latency of structures associated with these aspects are potentially key parameters in achieving high performance. The scheduling window consists of instructions renamed but not yet issued to the execution time, and is examined each cycle to find instruction for each use. We saw that while scheduling windows are important, their size is not the most critical issues. When building a high performance large instruction window processor, branch misperfusion expose the log latency association with a high frequency deep pipelines and are the single largest contributor to performance degradation as pipelines are structured. Branch misperfusion degradations as a recovery requires a redirecting fetch to the correct instructions and restoring the rename map. Table FIBO new instruction can be renamed. The map table can be restored from a checkpoint, incrementally restored from a non-SAV map tables, such as that retirement register alias tables, incrementally restored from a history buffer that shows the speculative map table updates performed since the mispredictive front was dispatched. In our proposed system, propose a confidence-based checkpoints and aggressive register reclamation. We show branch recovery mechanism to be critical for high performance, and show a recorded buffer based recovery mechanism to be a performance limiter. Instead of using a ROP, we propose selectively creating algorithms at low confidence branches. Our selective checkpoint mechanisms enable fast branches misprediction recovery and minimize checkpoint overhead. We show each checkpoint and sufficient to achieve most of the performance of 2048 entry instructions window for processor with an ideal branch misprediction recovery mechanism. In combination with a checkpoint based recovery, we decouple register reclamation from the ROP. Now we are going to discuss about the flow diagram of our process. In our flow diagram represent the flow of our process. First of all, we give the input to the address calculation, then we generate the index and offset, then finally we give the input value to the KM array, then array will convert into priority index table. Then finally we pass the input into the encoder. The encoder divided into two parts, address decoders. These inputs give it to two address decoder. Then finally we generate a tag array and a tag array, and data array output finally pass it into the page mapping, and finally we give the rename of our process. In our another kind of address decoder, give it to the tag array. The tag array generates the different kind of array values. The array values give it to the where tag array. The where tag array identify the patch mapping condition. The patch mapping finally passes into the remap condition. Finally we got the different rename conditions output. Now we are going to discuss about running procedure of our project. In our project we have four steps. First step we check the syntax error, then second step we generate the Addons schematic diagram, then third step we generate the technology schematic diagram, then finally we generate the simulation waveform. First we select implementation, select main function, then select check syntax. In this step we check the syntax error of our program. In case of any error and warning there, please show in our console block. In our program we have no error. Now we are going to the second step. Select view Addons schematic and run that. Now we generate the Addons schematic diagram. Please wait. Then select add, then create schematic. This is our overview Addons schematic diagram. Address, data, clock, enable, these all are our input signal, data our output signal. This is our internal block diagram of our Addons schematic. This is our internal block of our Addons schematic diagram. Now we completed two steps. Now we are going to the third step. Please wait. Select technology schematic diagram and run that. Add, create schematic. This is our overall technology schematic diagram. Now we completed three steps. Now we are going to the final step. Select simulation, select main function and simulate behavior model. Now we are going to generate the simulation waveform. Now we give the initial condition of our program. Clock value set to 0. Address value give any randomized signal and enable value set to 1. V value set to